We continue with the curiosity when we apply these geometric series, and we will see how to get a ratio of integers out of a number that is repeated. So let's say we have a number 0.7777, so this is 0.777 and 7 forever. It never stops, keeps going like this. So we would like to write this as a ratio of two integers, so A over B, some number upstairs and some number downstairs. And we will do that using geometric series. So what we realize here is that 7 is repeated, that's true, fine. Now 0.7, that's 7 divided by 10, like this guy. Plus, this here is 7 divided by 10 to the power 2, so 10 to the power 1, 10 to the power 2. This position here, 7, 10 to the power 3, plus fourth position, 7 divided by 10 to the power 4. Fifth position, 7 divided by 10 to the power 5. And it keeps going like that. Again, this is a geometric series. So we use geometric series. Just as a reminder, the geometric series, the general form is something like this, argument and then the common ratio. So we have A plus AR plus AR squared plus AR cubed plus AR to the power 4, and it keeps going. So what matters is to identify A, the first part of the first component of the series, the argument, and to identify the ratio. And we know that when the ratio is smaller than 1 in absolute value, the series is convergent. So it converges, and the sum is, so the sum is given by a formula A, that's why we need to identify it, divided by 1 over R. Here obviously R is smaller than 1. If R is greater or bigger than 1, the series is divergent. So here we need to identify A. So here, just to rewrite maybe 7 over 10, there's the first guy. So we need 7 over 10 times something to look like 7 over 10 to the power 2. First error. So 7 times 1 is 7, 10 times 10 is 10 to the power 2. Fine. 7 over 7 times 1 over 10 to the power 2. The third guy. This guy, 7 over 10 times 1 over 10 to the power 3, and it keeps going. So here we identified A, this is our A, 7 over 10, and also we identified R, AR, 1 over 10, which is smaller than 1 obviously. So the series is convergent. That's beautiful. So it's convergent. Fine. And we know what's the sum. So what's the sum? The formula is A divided by 1 minus R. Our A is 7 over 10 divided by 1 minus R. R is 1 over 10. So we have 7 over 10 upstairs. Here we have 10 minus 1, so it's 9 over 10. So 10 and 10 go. We have 7 over 9. So our number 7 repeated forever, right? 7, 7, 7 repeated forever is actually equal to 7 over 9. So integer, integer. So very nice. So this is an application of geometric series. Just write the things properly and then, so here 0.7, this guy is 7 over 10. This one is, so this is, if I have this number, this is 0.7 plus 0.07, right? So this guy here is 7 over 10, and this guy here is 7 over 10 to the power 2. Now if I have 7, 7, 7, the first guy is 0.7 plus the second guy is 0.07 and the third guy is 0.007. So that's where it comes from. So divided by 10, divided by 100, divided by 1000. It's better to write the exponents. So that's how we got all of these numbers here. Okay, so let's make up another number and see what will happen. So let's say I use another number. So you see these numbers with repetition can be written as fractions, so that's beautiful. So let's say I have 3.2, 5, and 2, 5 is repeated. So I have 3.25, 2, 5, 2, 5, 2, 5 forever. Okay. So this is equal to 3 plus 0.25, 25, 25, 25 forever. So the 3 in itself is fine, we will keep it. This part here we will rewrite it as a fraction and see what happens. So 2,5 is what is repeated. So I have here 0.25 plus 0.0025 plus 0.000025. So if I want to write it this way, that's what we would do. So I have here 25 divided by 10 to the power 2 for the first guy, plus 25, this is the repeated part, so 1, 2. And then the next guy is 10 to the power 1, 2, 3, 4, plus 25, so the position 1, 2, 3, 4, 5, 6. So you see we are repeating two numbers, and look at the powers, 2, 4, 6, so the next one is 10 to the power 8, and it keeps going. Okay, so again 3 plus. This baby here is my A, right, for my series. So I would like to factor it here also, so 25 over 10 to the power 2, so I have 10 power 2 downstairs, plus 25 10 to the power 2. So here I'll have 1 divided by 10 to the power 4, plus, so we write a couple of them just to see the pattern, and then we leave it alone. So here, this piece is my geometric series, right? 3 plus, well 3 we will edit, no problem, but this this is my geometric series. So here, A is 25 over 10 to the power 2. Okay, you can, maybe this one is okay to write, maybe it will simplify a little bit. But in general, if things don't simplify, if I had, instead of 25, 27, I couldn't simplify anything, I would leave 27 over 10 to the power 2. But in this case, I'm able to, so I'm doing it, it's fine. And R, this is our R, is 1 over 100. So this is smaller than 1, obviously. This means that this series here, geometric series, is convergent, and we know the sum. So this is 3 plus. So the sum of this geometric series is A divided by 1 minus R, which is, so A is 1 over 4 in this case, because it's easy to simplify. Otherwise, I would keep this expression here, and we will struggle with it a little bit. 1 minus R, so 1 over 100. So 3 plus, again 1 over 4. Here is 100 over 100, that's 1. So 100 minus 1 is 99 over 100. So here we have the 100 goes up. We have 4 times 99. Now 100 divided by 4 is 25. Oops, I forgot the plus 3. Oops. So 3 plus 4 times 99, and then 100 upstairs, plus equal 3 plus. So here we had 25 over 99. So 100 divided by 4. So here we are. We're almost there. Now we have, our goal is to get the ratio of 2 integers. For now we are not yet there, so we put this on common denominator. So I have 3 times 99 plus 25. So now I'm going to end up with one number upstairs and one number downstairs. So this is 300 minus 3, so 297 plus 25. So this is 322. Now sometimes we are able to simplify things. If we keep simplifying, it's fine. If not, we keep the number as is. So in this case, finally, we can say that 3.25 repeated is equal to 322, obviously we don't make any errors, divided by 99. So integer, so ratio of 2 integers. So when we are asked to write number with repetitions in terms of ratio of 2 integers, we go through these geometric series. So let's do another one with maybe 3 digits repeated, just for fun. So maybe I'll also move the place where the repetition happens. So let's say we have 2.4, and then let's say repetition happens 217. I just make up stuff. So this is 2.4 plus 0.0217 repeated. Right? 2.4 is fixed, and then 217, 217, 217, 217, 217. That's what's happening. Right? So this is 2.4 plus 0.0217. 217, and then 217, 217 forever. So in this situation, our 2.4 stays in front, there's no problem. Now here I have my 2.217, that is repeated, fine. Now what are the positions? 1, 2, 3, 4. So 10 to power 4 plus 217 position 1, 2, 3, 4, 5, 6, 7. 10 to power 7. So you see three numbers are repeated, 4, 7. So the next guy will be 10, and it keeps going. Again, 2.4 stays, and I have my first member of the geometric series. So this is my A. So I need to factor it from here so that I will have A times R. So that way I will know who is R also. 10 to power 4, 217, 10 to power 4 times 1, 10 to power, so to complete is 3. Plus 217, 10 to power 4 times here to complete 10 to power 6, and it keeps going. Right? So here A is 217 over 10 to power 4. So here you see I cannot simplify much, so I'll keep it as is. And R is this value here, 10 to power 1 over 10 to power 3. So this is still smaller than 1. So this series, geometric series, is convergent because the common ratio is more than 1, so we can find the sum. So we have 2.4 plus, and the sum of this geometric series is A divided by 1 minus R, as usual. So we have 2.4 plus. Now A is 217, so now it's just copy paste. 1 minus 1 over 10 to power 3. So now it's just a little bit long to write. 10 to power 4. Here we have 1000 minus 1, so that's 999 divided by 10 to power 3. So things can simplify a little bit. Here 10 to power 4, 10 to power 3. So I'll have 10 here only. So I'll have 9990, and the upstairs will be 217. So essentially this, and then this guy goes up, they simplify. So I'm almost done, but I'm not done yet. So 2.4 is 24 divided by 10. Just to write things without decimals. So now I need common denominator for both. So that will be 9990. So how do we do here? We need to multiply by 999. So 24 times 999 plus 217 equal. So we need to multiply this. So this will be 24,000 minus 24. So 24,000 minus 24 plus 217. So essentially we need to take care of this, so it will simplify to 23,900. So how much is this? Oops, it's adding. I'm subtracting instead of adding. So these two, I'll get 24,000 plus 17. So minus 6, 200 minus 6, 194. So this will be 24194 if I don't make any errors. So this baby will be 24194 over 9990. So now, essentially, if I didn't make any errors. That's our ratio of two integers. Sometimes it's possible to simplify, so we can simplify things. If we divide by 2, both of them are divisible by 2, so we can simplify further. But that's the procedure, the idea. Always check the part that is stable and then the repeated part. Here, repeated part is happening on the digits from 2, 3, 4. So 217 divided by 10 to the power 4. That's why we do this. So maybe I'll just write another one to split it like this, and then you complete the process. So let's say I'll make up something, maybe further down the line. So let's say 12.31, and then let's say 2, 4, 5. Let's say these 3 repeat. So what do I have here? I have 12.31 plus. So I'll write this a little bit just to see what it is. 0. So these 2 zeros, and then I have 245, and then 245, 245 forever. Okay, so I have fixed part 12.31. I'll need to treat it at the end. It's fine to put the common denominator and everything. That's okay. But I'm taking care of this now. Plus. So I have 245 divided by 1, 2, 3, 4, 5. So 10 to the power 5. Right? 1, 2, 3, 4, 5. Plus 245. So these 3 here. So 1, 2, 3, 4, 5, and then 1, 2, 3. So 10 to the power 8. Again, since I'm repeating 3 digits, the powers go 5, 8, and then 11, and then plus 3 again. If I'm repeating 4 digits, well, here I'll have 4 digits, and then it will be, let's say, 5, 9, 13, etc. So it's essentially just pay attention to these small details. So the fixed part stays. Now this here is a geometric series. So we see that A is 245 divided by 10 to the power 5. And so I will need to factor it here also. 245 10 to the power 5 times 1. So 10 to the power 3 here now. Downstairs has power 5. Power 8, sorry. 245 then 5 times 1. So we are 3 plus 3 is 6. So if I look here, 5 and 6 is 11, and it goes on. So now here it is clear that we have a geometric series with A 245 over 10 to the power 5, and this is R 1 over 10 to the power 3, which is smaller than 1. So the geometric series is convergent, which means that this piece here is equal to 1231 plus A over 1 minus R. So 1231 plus A is 245 over 10 to the power 5 divided by 1 minus R. R is 1 over this. So now it's a little bit more complicated. 245 over 10 to the power 5. Here I'll have 10 to the power 3 downstairs, and it will be 1000 minus 1, which is 999. Okay, fine. So if I write this piece a little bit, so I have my 1231 plus, if I try to combine this into a single fraction, I'll have 999. So times this, times 10 to the power 5 downstairs, and upstairs will be 245, times 10 to the power 3, so things will simplify a little bit, 10 to the power 3, 10 to the power 5 downstairs, so I'll have 2 zeros downstairs. So now the next step is to write all of this on a common denominator. I'll just rewrite this properly. So instead of having a decimal, I'll have something like this, which is the same thing, it's just a fraction, and it's easier to deal with this fraction. So now the common denominator, so it is 1231 times 999 plus 245. So now we just need to compute this, and we will get some number here, p over 99. So we need to compute the p, multiply this in the calculator, and you get the number. Okay? So that's the idea. It's a curiosity that helps us write these decimal numbers with repetition in terms of a fraction.